Hi,
Hey,
Lee.
hi, Louis. How are you?
I'm good.
Good. Let's do some circuits.
Great.
Look at what I have here. On the left, I have two light bulbs connected to a battery, 12 volt, and parallel. So I drew the circuit diagram. In parallel, what it means is that both light bulbs are directly connected to the battery. So they're both going to get 12 volts because the battery is a constant source of voltage. And the other side, on the right, I have the same light bulbs, but this time they're connected in series, or they're connected one after the other to the battery. So the current will go from one and then the other. So that means they both together they get 12 volt, but individually they'll get essentially half because they're again identical light bulbs. So, and then they should then appear differently, right?
Let's just check it out.
Yeah, you're right. Let's just check this out. So, all right, batteries on the left here. Whoa, that's bright. Two light bulbs, both directly connected to 12 volt. Pretty visible. Then I connect to the right side, and this is in series. Much less bright.
Yeah, but what's going to happen if you short one of them?
Well, let's try. So, you mean like if I get rid of this one,
Yes.
and I just connect this single one to the battery? Well, it should be the same as the parallel, I think. Yep. This is then because this light bulb again is receiving the full battery, this full 12 volts of the battery. Cool. Can you explain this?
Yeah,
All this behavior?
Let me take that to the blackboard here. So the power dissipation in each light bulb is equal to the current through the light bulb multiplied by the potential difference.
Right.
And through ohmic now, we know that the potential difference equal to the current multiplied by the resistance here.
Right.
So if we just plug this in, we get the power dissipation equal to potential squared divided by the resistance in each light bulb.
Perfect. And that totally makes sense now. Okay, so you're saying that the power dissipated tells us how much energy per second is being used, so that should be directly related to the brightness. And the power dissipated is proportional to the potential difference square divided by the resistance. These are all identical light bulbs, so they all have the same resistance. So then the only issue is how much voltage are they getting. These two are getting 6 volts because they have to split the battery into two light bulbs, versus the parallel ones are getting the full 12 volt because it's not being split. So therefore, they look brighter. What do you think you have in your house? This kinds of circuits or the series?
It must be in parallel.
Must be in parallel, exactly, because when you're in your house, and let's say you turn on the kitchen lights, and then you decide you're going to turn on the living room lights, you don't get two dimmer light, right? You get two identical lights. So everything in your house is in parallel. It must be. Cool. Now let's do a cool circuit. The most important part of a circuit is always remember that it needs to be close. If it's disconnected, you don't get anything. So here I have a fun little ball. It has just an LED that flashes in it, and it has two little metal connections. And so in order to get a current in a circuit, I just need to connect these two metal. And it turns out that we, as humans, are conductors because we have a lot of ions and water in our body. So I can use my own body to connect from one end here to another and light it up. And in fact, we could do this with multiple humans. So I can go and hold this way. Having some issues here. Maybe a little bit down. All right. Pause for the. Yay! And we're closing the circuit.
That's really cool.
You can go here, you can go there. But what if we try the table?
Let's try it.
Doesn't work. The table is not a conductor, we are. What about the metal here? Or here? Or again, the best is this way. That's electricity. Circuits, yay!